Welcome to the Trainee household. My name is Erica Trainee, and today we will be investigating the heat flows of my home here in southeastern Connecticut. Before we begin, I'd like to point out some important figures to keep in mind. For one, my home has a total area of 2,700 square feet. It's a balmy 48 degrees Fahrenheit out today, and about 15% of the external walls of my home are made of windows and doors. These numbers are very important as they will be used in many of the calculations we will be making today. Let's begin. Okay, so here we are at the front door. As you can see, we have the main door and the storm door. The main door itself is about 1 3/4 inch thick of just wood. Without the storm door, the rate of heat flow through the main door would be around 149 BTUs per hour. However, with the extra added insulating effect of the storm door, that decreases to around 90 BTUs per hour. So even though we have that storm door here at our front door, the maximum insulating effect of that storm door cannot be reached. Because here, as you can see, due to some settling of the house, we've got infiltration, areas where some of the heat from the inside of the house can escape to the outside. Okay, so here we are at the back door of the house. I like to consider this back door as more of a window because it's a large pane of glass and a second large pane of glass with an air gap in between. However, this door is pretty unique because it's got these lines on the inside that you can adjust. So when you have them fully closed like this, it creates two smaller gaps of air and prevents the air from moving even more. Preventing air from moving in small spaces helps prevent convection of heat. Okay. So here we are at one of the windows of the house. All the windows in this home are double pane with an air gap in between. Like the back door, that air gap helps prevent heat transfer through the window. However, this could be improved if you had double or triple pane glass with argon in the air gaps in between. This is because argon allows less heat to flow through. There are around 14 windows in this house this size, which makes a total of 1,700 BTUs per hour lost through the windows. Another important thing to consider when looking at the windows of a home is what the framing is made out of. Here we have wood and vinyl framing for these windows. Therefore, for a double pane window with this type of framing, it gives these windows an R value of 2. So since we've been talking about the windows, now would be a good time to talk about the orientation of the house and how that affects the windows. So right now we're facing the south side of the house, so all of these are south-facing windows. Therefore, during the summer, the sun is higher in the sky, and that overhang helps to prevent some of those sun rays from going into the home, therefore reducing the cooling load of the home. However, that could be made better if that overhang were a little bit larger. In the winter, these south-facing windows get a lot of sun because the angle of the sun in the sky is a lot lower, and that helps to heat the home. Headed in this direction, towards the east and north side of the house, it would be better to have windows with a low emissivity coating on them. This coating would be permeable to visible light, therefore allowing light into the room, but preventing heat from coming into the house as well. Now I'm going to talk about the ceilings and the attic of the house. Insulation with a much higher R value is used in the ceilings because heat rises, and therefore the ceiling would be a great place to lose heat in a home. So you want to make it extra insulated. The attic has this layer of plywood here, and then above that there's 2 layers of black shingles. So although that's one way to insulate the home, in another way the 2 layers of black shingles is almost worse for the home because in the summertime the black color of those shingles helps the house to absorb more heat, whereas if you had something more reflective, that helped the house stay cool in the summer. So here we are in the basement of my house. As you can see, it's slightly above ground, so this wall right here is where the foundation of the house lies. That means that some of this wall is concrete exposed to air outside. This is a pretty poor insulator. As the air goes by the concrete on the outside of the house, it picks up heat from inside the house and takes it away because there's nothing keeping the air still right against the concrete. The concrete also has a pretty high thermal conductivity. 12 BTU inches per hour degrees Fahrenheit foot squared. So here in the garage you can see how the foundation of the house is concrete and exposed to external air a little bit better. So this is the same in the basement, only it's not covered up by a wall. Down here in the garage, you can really easily see the external walls of the house. These external walls are made up of 2x6 studs, 24 inches on center, and it has R19 fiberglass insulation that's 6 1/4 inches thick in between. So using the framing factor of 0.12, the R value of that section of the wall, or that layer of the wall, is around 17. Behind these layers is about an inch of exterior plywood, some building paper. On the inside of most of the house, there's the gypsum board, and then on the outside, there's the vinyl siding. So taking all of this into account, I calculated that for every 2-foot section of this exterior wall, around 10.3 BTUs per hour are lost. Welcome to our furnace room. To heat our home, we use forced hot air with oil as the fuel source. Our oil tank is located external to the house. Comes in through these pipes here. They follow around. They get sent through a filter and then to a pump where they're atomized. They're ignited here in this hot box. A blower sucks in air from the inside of the home. It passes through the heat exchanger, picks up heat, and then gets sent out to the home. Here is where exhaust from the combustion is taken and sent out through the chimney. This represents a spot in which heat could be lost that is not being sent into the home. Furthermore, another way to make this whole system more efficient would be to insulate this ductwork that's sending heat out to the home. Make sure none of it is lost down here in the basement where it's not needed. Infiltration is another way in which a home's thermal efficiency can be reduced. As we saw before, here is the spot in which the house has settled, opening up a crack in the frame. Pressure differences between the inside and the outside of the house causes air from inside the house to leak out. This type of infiltration can be mitigated. For example, it looks like my dad has put some insulating foam in this crack to reduce its infiltration. Taking into account the amount of oil used to heat our home this year, as well as the square footage of our home and the amount of electricity delivered to us, BU's Energy Use Intensity Calculator shows that our EUI is around 48 kilobtu per foot squared. Compared to other building types' average EUIs, listed on Energy Star's website, this value of EUI is not too bad. However, it should be noted that there are other buildings that may use more energy than a residential building would. For example, a hospital or a school. Either way, a home's EUI is a good way to look at how the heat flows within a home impact its overall energy use. So, in conclusion, we've looked at the heat flows in my home, how the state of insulation can be improved, how my home is heated, and then we calculated the energy use intensity of my home. And here's my cat chat. Thanks for watching.